HVZ reaction. Abbreviation for this is Hell or Hard Zelensky reaction. Or simply we can say this one as halogenation of carboxylic acid. In this reaction, we will do simply halogenation. Means simple addition of halogen. So let's see what are the conditions and what is the mechanism behind this reaction. So first let's see what is the reaction. Let's take any carboxylic acid, but few conditions are there for this. This is our functional group, C double bond OH. So next to that one, we'll call it as alpha. Okay, whether R may be an alkyl group or simple H also, no problem. But our condition is alpha carbon should at least have one hydrogen. This is the first basic condition. So this is the basic condition. What is the condition? Alpha carbon atom should contain at least one hydrogen atom. Next, what are the reagents involving in this reaction? This is also very important. Simply they will give reagents and the reactants and reagents, and they'll ask the product names also. So let's see what are the reagents involved in here. So first one is red phosphorus, which we require in small quantity, and of course our halogen. This halogen may be chlorine, bromine, anything. And the second one is, as we all know, simple hydrolysis. So what's going to happen in this reaction and what is our product? So observe the difference between the reactant and the product. What happened here? Simply in the alpha carbon atom, one H is replaced by one halogen. Means what is the product name? Alpha halo carboxylic acid. This is our product. This is the simplest reaction. But the condition is alpha carbon should at least contain one hydrogen and red phosphorus plus halogen. Halogen may be chlorine or bromine, and the next condition is water, hydrolysis. So now let's see the mechanism. Now tell me, in both the hydrogen, which one is more acidic? Obviously, this hydrogen is more acidic. So why can't this halogen add to this C double bond O? Instead of adding here, why it is going to this carbon? Why it is going to replace this hydrogen and adding at this alpha position? First preference is at this position only. But now the preference goes to this alpha carbon atom. Why means, okay, that's the correct thing. This is the more acidic one when compared to this one. But during the mechanism, we'll eliminate this hydrogen first itself. Why? Because we need halogen attachment at the alpha position. So now let's take the mechanism one by one. So what is our carboxylic acid? RCH2C double bond O OH. Now what we are going to use here? Red phosphorus plus halogen. If we take PX3, that is phosphorus trichloride, trihalogen halide, or otherwise, if we take 5 moles, this one, PX5 also, phosphorine pentachloride, pentahalide. So we studied these two reactions, and one more thing is with SOCl2 also we studied. But here we are going to take these two reactions. Here no problem. Anyway, we can take PX3 or PX5 also. So now let's take PX3. This is our first condition. small amount of red phosphorus and halogen. So what's going to happen here? Simple thing. Hydrogen will be replaced by chlorine. Why we are doing like this? Because we are eliminating the more acidic hydrogen. So our first purpose is to eliminate this more acidic hydrogen with the halogen. Now what happened? Obviously this hydrogen becomes more acidic one. So what is the next procedure? Simple one, as we all know. We need C double bond OH here. So for that, what's the internal rearrangement happens here? Simple tautomerism going to happen here. So how this going to happen? Obviously, this double bonds goes here. We know this is partial negative charge, partial positive charge. As halogen is a good leaving group, it goes out. So to satisfy the positive charge of this carbon atom, this hydrogen sacrifices its electrons and forms a bond between these two, and this H plus needs electrons, so it goes and adds to this oxygen. So what finally we are going to get are CH double bond, as these electrons goes and forms a double bond between this C and C, R CH double bond C X as it is here O and H. So what is this product name? This is enol. Now what happens? Donation of electrons is needed, obviously, but is this carbon is able to donate electrons? No. Why? Because it is surrounded by two more groups. One is halogen and one is OH, oxygen, which are more electronegative things. So the bond will break here, and the electrons are donated by this carbon. No, but not by this carbon atom, because this is bounded with two greatest electronegative groups. So here what happens? Our X2 comes here. First of all, this X2 don't have any polar dipole, but whenever it comes to nearer to this pi bond, it also started showing dipoles. So what happens? As this oxygen is having lone pair of electrons, this bond goes here, and this oxygen donates the lone pair of electrons to this positive charged carbon. So then one of the positive charge goes here and one of the negative charge goes here. But this X and H goes out as minus HX, leaving R CH. X came to this position, CH, C double bond O and X. So minus HS goes out, HCl or HBr goes out. So in this case also same thing. This carbon is electron deficient. So what happened here? Our water comes into a play. So what is the water formula here? This is having lone pair of electrons. This oxygen attracts the pi electrons, and this X as a good leaving group, it goes out. Again, to balance the positive charge, this oxygen again throws back its electrons, and this oxygen forms a bond with this carbon to satisfy the positive charge. So RCHX as it is leave, C double bond O, C double bond O as it is leave. First it attracts towards it and then it gives back to satisfy the positive charge. Now H2O. So this finally, this OH, this bond goes to satisfy the positive charge of oxygen, finally giving our alpha halo carboxylic acid. This is the HVZ reaction, or simply we can say that as halogenation of carboxylic acid. Instead of adding the halogen at the COOH place, it goes and attacks the alpha carbon atom, forming alpha halo carboxylic acid.